Okay. Optimization. What does optimization mean? Optimistic. Being positive. I like where you're going. Let's stay optimistic with our optimization. Okay, if I want to optimize something, optimize to make it efficient. Okay, good. So if I want something really big, what would be a word that I would use to optimize it? Okay, well, scratch that. Profit. If I want to optimize my profit, what kind of profit do I want? Big. Okay. I would want to maximize my profit. Do you agree? What about costs? If I want to optimize my costs, we would want to minimize them, right? Okay. So words we're going to associate with optimization are maximize or minimize. Okay? When you see the words maximum, minimum, maximize, minimize in your problem, you know that we're working with an optimization problem. And today we're going to solve optimization problems with linear programming. Okay? So these are the steps that we're going to take, and they're written on there for you. Okay? So, do you remember how I kept saying that today we're going to be doing the same thing as yesterday with one extra step? Your one extra step is this idea of the objective quantity. What are we maximizing? Okay? If we are maximizing the profit, you're going to have to write a profit equation. If we are minimizing cost, we would have to write a cost equation. Okay? Then you're going to do the same thing as before. You're going to set up your constraints. Okay? So your inequalities, like we did with number 65 and 66. You're going to graph your inequalities, just like you did with 65 and 66. You're going to find your vertices, just like you did with those two. But then, going back to this objective quantity, we're going to take those vertices and we're going to plug them in to either like that profit or cost equation so that we can decide what coordinates or what piece of information will actually give us the most for our profit or the least for our cost. Okay? So before we actually get to apply any of that, let's just practice everything except setting up the constraints. Okay? You see on the front side of your note sheet that there are two problems where I already give you the constraints. Okay, so let's go to that first example. Okay. Now, this z equals 3x plus 2y that I highlighted up here, that is your objective quantity. We're going to come back to that later. We do not graph it. Do we graph it? No, we only graph the inequalities. Okay? So, x is greater than or equal to 0, y is greater than or equal to 0. What does that restrict us to? Quadrant 1. Okay? Okay. Not a whole lot of fun yet. All right. X plus 2y is less than or equal to 4. I'm going to graph that in blue. Okay? This is an equation. You are welcome to put it in slope-intercept form, but you're also welcome to use the intercept method. If we plug 0 in for y, what is our x-intercept? It is 4. If we plug 0 in for x, what is our y-intercept? It is 2. Okay, and if you've got a ruler, all right, Callie, which way are we going to shade? Okay, so we're going to shade towards 0, 0?
Yeah.
Okay, so I'm going to shade towards 0, 0, and since I already know that we have to stay in the first quadrant, I'm going to just go ahead and shade in this triangle, because there's really no point in me shading anywhere else. Okay, now, some of you may choose not to shade until the very end, and that's fine, but just for visual purposes, I'm going to go ahead and do that for this problem. All right? X minus y is less than or equal to 1. So let's just focus on the equation. If I plug a 0 in for x, what is our y-intercept? -1. And if we plug a 0 in for y, what is our x-intercept? +1. Okay, so with your ruler, okay, so now I need to determine where to shade. Courtney, which way are we gonna shade? Towards 0, 0. So we're gonna shade this way?
Yes.
Okay, so if you are not shading until now, that dark blue is our area. Just like we did yesterday, we need to find our vertex points. Turn to your neighbor. How many vertex points do we have? Okay. Tiger, how many do we have? 4. Okay. We have one right here. That one is obvious, don't you think? The one I highlighted in green? 0, 0. Okay. This coordinate right here, we know what it is. What is it? It's the coordinate 0, 2. Okay. We plotted that point when we did the intercept method. Okay. All right. This point right here, we also physically plotted for an intercept. What is it? 1, 0. Okay. Now this coordinate looks like it could be nice. What does it look like it could be? It looks like it could be 2, 1. Do I want you to write 2, 1 and then move on? Let's imagine them as equations. That is the intersection of the blue and the red line, which really are only lines with slope. But if we imagine the equation, 1 times 2 plus 2 times 1, does it equal 4? Yes. Is 2 minus 1 equal to 1? Yes. Okay. All right. This is where we stopped. What? It did. It was because I did the highlighter, and I highlighted, right? Okay. So this is where we stopped yesterday, but now in a linear programming problem, when we have an objective quantity, we're going to plug our vertices in to our objective quantity. Okay? So, Z equals 3 times X plus 2 times Y. If we plug in the coordinate 0, 0, what do we get for the objective quantity? 0. If we plug in 0, 2, 3 times X plus 2 times Y. What is our objective quantity for that vertex point? We get 4. Okay, we're going to do this for all of them, right? Our objective quantity, 3x plus 2y. When we plug in the coordinate 1, 0, we get 3. And then finally, 3x plus 2y. When we plug in the coordinate 2, 1, we get 8. Okay. Now, this is a pretty generic problem. I gave you the constraints. I gave you the objective quantity. What we practiced was actually graphing it, finding the vertices, and plugging those into the objective quantity. Once you have plugged your vertices into the objective quantity, and I can see that you did that, now, some of you are going to be doing work either in your head or in your calculator, that's fine, but I at least need to see that for 0, 0, your objective quantity was 0. For 0, 2, your objective quantity was 4, etc. I know that some of you may not write out the work, but I need to visually see that you found all 4 of those. You understand? Okay. So now, what is the minimum we have for our objective quantity? What's the smallest number? Okay, so we have a minimum of 0 at the coordinate 0, 0. And we have a maximum of what? 8 at the coordinate 2, 1. Okay? So why these vertices are important is because they're like our outermost points of our bounded region, right? And so if we can take our outermost points of our bounded region, we have the smallest point and the biggest points somewhere in there. They can help us find our minimum and maximum values. Okay. Questions before we move on? Okay. I hope you're not working too far ahead because there are really only 3 equations, 3 inequalities. You have like a 4th one for some reason, so please cross it out. But x plus 3y is greater than or equal to 15 should not be there. Okay, are you ready? Our objective quantity is z equals 4x plus 2y. And we have 3 inequalities to graph. So what I'm going to do is I'm going to do them each in a different filter. Okay. All right. X plus 2y equals 4. This is a nice one to do the intercept method on. Do you agree? What is our y-intercept? 2. And what is our x-intercept? Okay, Eli, which way are we going to shade? Away from 0, 0? Okay. And if you don't want to shade till the very end, I don't have a problem with that. Okay? All right, 3x plus y is greater than or equal to 7. Now, here is one where the algebra to put it into y-intercept form is really not that bad, right? Y equals negative 3x plus 7. Okay, that's not bad. Do you agree? It's one little move. Okay, so we have a y-intercept of 7. And we have a slope of negative 3. That's not a slope. Sorry. Which way are we shading? Away again? Oh, come on. Shading away? We are shading away. All right. Have fun. It's like one of my favorite things to teach because I get to play with all these colors. Okay, now, next one. Okay, intercept method. We can do the intercept method here, I think. What is the x-intercept for this third line? -7. What about our x-intercept, or our y-intercept? Okay. And which way are you shade? We're going to shade towards this time, don't we? Yes, no? Okay. So, our solution is what we have in the black area. Okay? And we are bounded by 1, 2, 3 vertex points. Okay? To save time, I will confirm to you what they are, but know that I would need you to actually plug them in. Okay? What does it look like they are? 1, 4, and that is correct. If you plug them into both lines, it works. What about another one? 2, 1. If you plug them into the 2 lines, it works. And then the coordinate 4, 0 is also 1. Yes. No, it's the intersection. But it's an intersection of, oh, it's not. Sorry, it's not a vertex. You're right. I think originally I had done the problem where the x-axis was 1, but it's not. Thank you. We only have 2 vertex points. Whew. Okay. Now, how does this one look different?
Unbounded.
It is unbounded. When we go to plug into our objective quantity is 4x plus 2y. So for 1, 4, our objective quantity is 12. And 4x plus 2y, when we plug in 2, 1, we get 10. So what is our minimum value? Our minimum value is 10 at the coordinate 2, 1. But what is our maximum? We don't have a maximum because this is an unbounded region. Do you agree this is going to grow, 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 grow? Okay. So we have no maximum because we have an unbounded region in the positive direction. Okay? If this were unbounded in the negative direction, we wouldn't have a minimum. All right. The time has come. We're all about the application, this chapter. Please read through example 3 on the back. No matter what, we have to define our variables for any application problem. So what are the 2 unknown items that we are looking for? What? Okay, so we're looking for the number of DVD player. I'm going to call it 1, and that's the $250 model. And then Y is going to be the number of DVD player 2, model 2, which is the more expensive one, right? Okay, so we have our variables. What are we trying to optimize? What are we trying to optimize? We are trying to optimize profit. So, our objective quantity must deal with profit. If you see the word optimize, maximize, or minimize, those are the 3 different words you're looking for your objective quantity. Since we're trying to maximize profit, we are going to write a profit equation that we'll plug our vertices into. So we yield a profit of $45 from DVD number 1 and $50 from DVD player number 2. So our profit equation is 45x plus 50y. Okay. Now we have to write our constraints. We have tangible items. What do we know about X and Y? They need to be greater than or equal to 0. Okay. We also know that the monthly demand will not exceed 250. The monthly demand will not exceed 250. Caleb, what can we do with that? Good. invest more than $70,000 in inventory. Well, DVD Model 1 costs $200 and DVD $250. DVD model number 2 costs $400, and we need the total amount of money to be less than $70,000. Okay, questions on where we got any of that? Okay, so let's graph it. I didn't provide you with a graph for a reason. I'm going to give you a little bit of freedom here. Okay, we know that we're restricted to the first quadrant, and so that's all I'm going to draw. Okay, now, in this line right here that I'm going to graph in red, our x and y intercepts are 250. Are you going to count by ones? No. I'm probably going to count by tens. Okay? Actually, I'm not going to count by tens. Maybe I'm going to count by 20s. Okay. Then, in the blue, I'll graph this one. Okay, help me out. If we have 400y equals 70,000, what's our y-intercept? Please help me out. What's 70,000 divided by 400? Okay. $175. And then if I have 250x equals 70,000, what's our x-intercept? What's 70,000 divided by 250? And since both of these two equations we would shade towards 0, 0, we have this right here. Okay. Okay. To save some time, I'm going to go ahead and tell you what our vertices are. We have vertices at 0, 175, 0, 0. That one was 25, 0. All of those you found when you just graphed them. Now this one right here, I will tell you right now, it is 200, 50. But you know that you could use substitution or elimination with these two right here to solve for that coordinate. Okay, it's not as obvious in this graph. Okay, what do we do with these vertices? Where do we plug them into? We got to go back to the equation that we wrote. In this case, it was a profit equation. So when we plug them into the profit equation, and this is what I mean, you can do it in your calculator, right? Where is it? 45x plus 50y. Here would give us $8,750. Here, our profit would be $0. 45x plus 50y here would give us, this is a 250. Was that confusing somebody? Apologize. 11,250. And then if we plug 200, 50 into 45x plus 50y, we would get 11,500. Do we care about the minimum in this problem? No. We care about the maximum. Okay? For a max profit of $11,500, we need to stock 200 DVD player 1 and 50 of DVD player 2. That is what that answer means. Much like last night, your homework consists of 5 problems, where the first 3 are just plain Jane problems. The first 2 are plain Jane problems. The last 3 are the application problems. Okay? Tomorrow in class, we are going to work more with these application problems. But please know that Friday's your test. So if you sit down to do this homework tonight and you're like, okay, we need to do a little damage control tomorrow. So if you have issues tonight, you know you can come in at 8:05 and spend 15 minutes working before class. Okay? Put my rulers in the bucket on your way out.